So this video is going to be showing you how to actually use the dot product and perform and use it to like do problems. So I'm going to show you and model for you exactly how I would show my steps within a reasonable limit to not take up too much time doing any problem, but still proving that I understand how to use the dot product and why I'm getting the answers I'm getting. And that's what I need you guys to show me, is that you know why you're doing things, not just that you know the final answer. That's what's important. So I'll show you a couple of shortcuts that I'm going to allow you to do when you're doing problems like this. So pay attention, and you can model my steps and do that when you're doing your homework or exams, anything like that. So we're going to use this example here. I have work, which is a quantity that is defined as a force dotted with a displacement vector. So F is a force vector. This triangle means delta, that means change. Whenever you're talking about math or physics terms, change in R, that's change in position. It's a fancy word just called displacement. So I have two vectors here, F and delta R, and work is the dot product between them. So in this problem, we are going to calculate work by performing that dot product. And then also we want to figure out the angle between vector R and the displacement vector F and delta R. So we're going to use the dot product a couple ways in order to do this. So our game plan, let's just put a plan to figure out how to do this. For number one, we're just going to distribute the dot product. So we have two vectors written in component form. We can distribute the dot product, use some definitions from the Cartesian coordinate system, get an answer. In step number two, we're going to have to also use the definition of the dot product. That the dot product between two vectors would be the norm of the first vector times the norm of the second vector times the cosine of the angle between them. So we want that angle. That's what we're looking for. So in number one, we're going to do the left-hand side. We're going to know what the dot product is. In order to keep on going and to get this angle, we are going to have to calculate the norms of these two vectors. Once we have that, then we can solve for our angle. So this is going to be a long problem, but I want to show you a few shortcuts you can take along the way. So these are my approved shortcuts for when you're doing problems. You are not allowed to do any other shortcuts other than this. So this is what I mean when I say you're allowed to do this. You can simplify your problem, but more than this is skipping steps, in my opinion. So remember though, if I ever say, especially on an exam, if I ever say show all steps, then you're not supposed to be using any shortcuts. I really want to see all of the steps. But if I don't say that, then you're allowed to use these ones. So the first shortcut is that when you are distributing a dot product, if you know a term is going to become zero because the dot product involves unit vectors like x hat and y hat, like when you're using two different unit vectors that are perpendicular to each other, if that's true, then you can skip the step where you actually multiply the numbers, the scalars, so that you can just kind of write that that term exists, but you know it's going to go to zero. So don't waste your time actually doing that much of it. So let me show you an example here. Let's say that we were distributing this dot product. I have two vectors here. The next step that I would do is I'm going to FOIL this out. I'm distributing the dot product. So I would do this, like this 5x hat term times this negative 8x hat term. That gives me negative 40 x hat dot x hat. The next term, I'm going to do the 5x hat dotted with the negative 1 y hat. I know that that's going to become a zero because x hat dot y hat is zero. So I'm just going to not even bother multiplying the scalars. I'm just going to get something x hat dot y hat. The next term, I'm going to have this 5x hat dotted with 4z hat. Again, you can skip multiplying the scalars and just show me that you see that it's going to be x hat dotted with z hat. And you can keep on going, and you'll notice that only 3 terms are going to survive that are going to involve dot products that are not perpendicular unit vectors. And so those are the only 3 that I'm going to actually multiply the scalars with. So this term, I'm going to move on to like the 3y hat dotted with the negative 8x hat. Again, that's going to be y hat dotted with x hat. That's going to go to 0. This next term, though, the 3y hat dotted with negative 1y hat, that's going to be negative 3 y hat dot y hat. That one I need to multiply by because that is not going to go to 0. All right, so that'll save you a little bit of time when you're working these problems. You can use that shortcut. The next shortcut that you can do is that when you kind of distribute that dot product out, when you see these terms that have a dot product with perpendicular unit vectors, you can do something like, I say that you can cross out the terms and write a 0. So notice that I still wrote those terms here, but now when I have like x hat dotted with y hat, I can show that that one's going to go to 0. So like this one right here, I can show that that's going to be a 0. I'm not going to make you write out the norm of this one times the norm of the next one times the cosine of the angle between them. You don't have to write that anymore. You can show me that it's going to 0 because you know that those two unit vectors are perpendicular to each other. Likewise, if you have an expression with dot products with the same unit vector, so like this one up here where you have x hat dotted with x hat, I know that that's going to go to the number 1 because the norm of x hat is 1, the norm of x hat is 1, and the cosine of the angle between any vectors that are parallel with each other, the angle is 0, so the cosine of 0 is the number 1. So that term is going to go to the number 1. So kind of similarly, you can show me somehow that these dot products are going to go to the number 1. They're not going to disappear, but that dot product is going to give you a 1. So again, so I kind of wrote it out a little bit more this time. So this term right here has x hat dotted with x hat. You can replace that with the number 1. This term has x hat dot y hat. That's going to go to 0. That one's going to go to 0. That one's going to go to 0. This one right here, that's going to go to the number 1. So don't forget that you're still multiplying that 1 by the scalar in front. So when you're simplifying these things, don't forget like this negative 40. It'll be negative 40 times the number 1 plus 0 plus 0 plus 0 minus 3 times the number 1. These next 3 terms go to 0. And then the last one I have negative 8. Z times Z is the number 1. So then I just get minus 8. So that's another, these are the 3 approved shortcuts you're allowed to use when you're working problems. It'll save you a little bit of time, but I need to see that you guys know why you're doing what you're doing. So I can't let you do too many shortcuts. So let's use them and let's do this problem. So the first step we're going to do is actually distribute the dot product. So let's find a vector f dotted with delta r. So I'm just going to copy down these things in component form. I'm going to skip writing the units. I'm going to save the units for the end. I know that f dotted with delta r is going to give me units of newtons n times meters. So in the end, my units are going to be newtons times meters. I'm just going to not bother writing those units over and over again. All right, let's distribute this dot product. So my first term, 3x hat dotted with negative 10y hat, that's going to give me something with a dot product that will eventually go to 0. So I'm not going to bother multiplying the scalars. This next term, 3x hat dotted with 3z hat, again, that's going to be x hat dotted with z hat. My next term, okay, now I finally get one. So negative 1 times negative 10 is 10 y hat dot y hat. Okay, so that's my first shortcut. I was allowed to do that. My next shortcut, I'm going to simplify this. And anytime I see a dot product between perpendicular unit vectors, I know that it's going to go to 0. And there where I see dot products with the same unit vector, those are just going to go to the number 1. So I can show that, so that's why some terms are 0 and why some terms are the number 1. And in the end, I get 10 plus 12 is 22. And like I said, the units would be newtons times meters because I had the units of the force vector were newtons and the units of the displacement vector were meters. So F dotted with delta R is 22 Newton meters. All right, so that's step number 1. We got number 1 done. Now the next thing we're going to do is trying to find the angle between these two vectors. We need to find the norms of these two vectors in order to plug it into the definition of the dot product. So let's do that. Let's try to find the norm of, let's start with vector f. So the norm of vector f is the square root of vector f dotted with itself. All right, so again, I'm going to skip multiplying scalars for terms that I know are going to go to 0. So I'm just going to do the first one here. It'll be 9 x hat dot x hat. The next one is just going to be an x hat dotted with a y hat plus an x hat dotted with a z hat. Okay, so I distributed my dot product, and now I am going to use the definitions here that any vector dot product with perpendicular unit vectors is going to go to 0. So that's why these terms are going away. And then my other definition is that a unit vector dotted with itself is just going to be the number 1. So I can simplify this expression as the square root of 9 plus 1 plus 16, square root of that, I get as 5.1. And this was the force vector, everything had units of newtons. So that's the norm of my force vector. Now let's find the norm of the displacement vector. Again, dot the vector with itself. And don't forget to take your square roots. So for this one, I'm just getting the square root of 100 plus 9. That is 10.44. And again, the units for this vector were meters because it was a displacement vector. So those are my two norms. I got my norms. Now this last step in order to calculate that angle, remember that the definition of the dot product says that the dot product between two vectors is the norm of the first vector times the norm of the second vector times the cosine of the angle between them. So let's solve this algebraically for the angle between them. So I'm going to divide both sides by the norms. And that will give me the cosine of the angle as vector r dotted with vector delta r, sorry, f dotted with delta r, divided by the norms of each of those vectors, so that the angle is actually going to be the inverse cosine of all of that stuff. All right, so now we can plug in our answers here. From that very first slide, we said that the dot product between these two things was 22 newtons times meters. The norm of the force vector was 5.1 newtons, and the norm of the displacement vector was 10.44. And so plugging that into your calculator, inverse cosine of 22 divided by 5.1 divided by 10.44, I get an angle of about 65.6 degrees. And that's my final answer. So now you're more equipped to do problems like this using the dot product and the norm, calculating these things, and you'll go a little bit faster by using these shortcuts. But again, you're still kind of showing me that you understand the concepts as to why these things are going to 0 and why they're going to the number 1. You're still showing me that, but within a reasonable amount of time. So these are approved shortcuts that you can use when you're doing your homework or when you're performing tests or exams, except on any statement or any problem where I explicitly say, show all steps. Otherwise, you are free to use these approved shortcuts.